Okay, guys, we're going to talk about chemistry today. Got a bunch of stuff to talk about chemistry. I'm going to probably split it up into two, perhaps three. They're going to be long, so just bear with me. And we're going to do our chemistry videos. So here we go. When we talk about chemistry, this is going to be kind of a need to know. I know I basically have a minor in chemistry. I probably had 16 courses of chemistry, 3 or 4 years of chemistry between undergraduate and graduate school. So you're going to get all the chemistry you need to know in about an hour, okay? So watch my video, look at my notes, and then go through the textbook, and if you have any additional questions, but don't get too bogged down in why and how, because that's a whole different level. So this is kind of what you need to know about chemistry. Basically, when we talk about chemistry, we're talking about elements. That's our building blocks, okay? All matter is composed of these elements, and elements can't be broken down. And if you don't know what an element is, let me see, you probably do, you just don't know you do. Carbon is an element, oxygen is an element, nitrogen is an element, calcium, sodium, potassium, sulfur, iron. All of those are elements. Now, that's not as small as they get. Okay, when we talk about elements, they're actually made up of things called atoms, and those are the building blocks. All right, atoms are things like protons, neutrons, and electrons. And if you're really a chemistry and physics nerd, you'll know that actually they go smaller than that. There's things called quarks and things like that. Don't need to know that. But for our purposes, the smallest thing is an atom. There are what you may have heard the word subatomic particles. Subatomic means they're smaller than atoms. When we talk about elements, we use their atomic symbol. So, for example, carbon is always written as C. Oxygen is O. I put on your study guide, there's about 20 or so elements that I expect you to recognize, not only their name, but their chemical symbol. So make sure that you look at that. This is kind of an old stylized way of thinking about the atomic structure of elements. This is hydrogen, this is helium, and lithium. And basically what you recognize is that they all have a proton. They may have more than one proton. They may have several. They may or may not have a neutron. Hydrogen does not have a neutron. Lithium and helium do. And they have an electron. Okay? As elements get larger, they have more protons, more neutrons, and more electrons. Okay, that's, if you ever seen the old periodic chart, the small ones, and then they just get bigger and bigger and bigger. And that just means they have more protons, neutrons, and electrons. The thing about these elements is that some of them, these atoms have charges. Protons are positive, electrons are negative, and neutrons are neutral. They have no charge. So typically, the atom or the element is neutral. Okay, one positive, one negative means there's no charge. This one you have 2 protons, 2 electrons, 2 neutrons. They cancel each other out, no charge. On this one, this actually may be a little bit negative. There should be another electron there. No, okay, 3 protons, there you go. 4 neutrons, so that cancels each other out. So 3 pluses, 3 minuses cancel each other out. So it's neutral. So you should see the same number of protons as you see electrons. When you don't see that, it's when you're talking about something called an isotope, and usually that does have a charge. That's when you're thinking about nuclear stuff, like if you have a scan with nuclear medicine, when they're doing imaging, there's usually some kind of radiation that they're using, and that usually means it has a charge. So your protons and electrons aren't balanced. I don't want you to get bogged down in atomic number or mass number and atomic weight, but for those of you who are wondering what those meant, that's just a way to describe the element, how big it is, what its size is. If you're talking about atomic number, you're talking about just the number of protons in it. If you talk about mass number, you're counting up protons and neutrons. And if you're talking about atomic weight, it's just the average. So again, don't get bogged down in that, but that's what those numbers, or if you ever see those terms, that's what it means. What I want to focus on a little bit are some bondings. When we talk about chemistry, all we're talking about is how elements come together, how they bond, how those bonds are made, and how they're broken. And that's how our bodies work. We're constantly making bonds and breaking bonds. When I eat meat, I'm breaking down, or any kind of food, I have to break that stuff down. And when I break down meat or sugars or fiber or whatever, I'm breaking bonds. When I'm building muscle or building bone or hair and nails, I'm making bonds. And there's basically three major types of bonds: ionic, covalent, and hydrogen. This is really stylized, this is your need to know, okay? An ionic bond just means that it's an electron transfer. So what that means is, here's my little orbital, planetary orbital model. And for example, if you're going to make sodium chloride, which is the same thing as table salt, basically you just take sodium, basically transfers an electron over here, okay? And like I said, don't get bogged down in the how and why. That's what's going on. That's an ionic bond. And these are pretty strong bonds. Usually when you have an ionic bond, it makes a crystal, okay? It makes a crystal. So things, all your salts, things like that are ionic bonding, and they're fairly strong. You have a covalent bond. That means electron sharing. And so, for example, on this one, instead of the electron going over here and leaving and being transferred, these are sharing. They're sharing these electrons. So in this case, if you put 4 hydrogens and they share their electrons with a carbon, CH4, that's methane. And those are fairly strong bonds, but not as strong as ionic bonds. A lot of our organic chemistry, which is kind of chemistry of life, things like sugars, proteins, things like that, have covalent bonds. When you talk about covalent bonds, they can either be polar or nonpolar. So polar or nonpolar. Polar means they have a charge, and this is no charge. And they don't actually have a charge. Let me kind of go back and explain what I mean by that. Carbon dioxide, basically, it's equal sharing. Okay, so there's no polar, there's symmetrical, everything's kind of evenly shared. In water, H2O, in water, the oxygen and hydrogen, they don't quite share quite evenly. And so what happens is it winds up making some charges associated with the water. So one side's slightly negative and one is slightly positive, but the overall effect is it's still neutral. Okay, does that make sense? You have a slightly more negative end and a slightly more positive end. The overall molecule is neutral, but there's a little bit of charge associated with that, which is handy when we talk about water because opposites attract, right? So minuses and positives come together. So if you take a bunch of water molecules, H2Os, the positives from the hydrogen will react with the negatives of the oxygen, and you will form these bonds. These are called hydrogen bonds. And that's how water molecules come together and attract each other. Opposites attract, they attract, and you form water. And that's one of the things that gives it the property of kind of having some tension, some strength. Water, if you think about a bug walking on water, it's because those hydrogen bonds are kind of holding those molecules together. But it's easily broken. I mean, you can splash in the water and the molecules fly apart. So it's not a real strong bond, but it's stronger than you think. All right, so that kind of introduces you to some basic chemistry ideas. Let's see if I can get out of here. Hang on. And I'm going to go ahead and start talking about I'm going to do this in 2 lectures, so y'all just hang with me. Let me open up my other PowerPoint. Let's see. Yeah. All right. You ready to go? So, get my pen back. We talk about chemistry, we talk about matter. I wish it would remember which color I wanted, but it won't. Okay. So matter. Anything that has mass, weight, and occupies space, that's a matter. Hopefully this should be real familiar to you guys. You've gone through elementary school and high school. You know that matter is solid, liquids, and gases. The best example of that is something that can do all that is water. When it's a solid, it's what? Ice. When it's liquid, it's what we drink. And when it's a gas, it's steam. So solid has a definite shape, liquid, definite volume, but it can change its shape. For example, there's water in here, so that has this shape of my cup right now. If I pour it onto the ground, it'll have the shape of the carpet that it's soaking into. And of course, gas has no shape, no volume. I mean, gas just kind of goes everywhere. Already talked about that. We talked about atoms. Take atoms, put those together, and build elements. So I've already kind of covered that. This is a periodic table. Again, it goes from small all the way down to big based on the number of protons and electrons that are associated with it. You don't have to know that, but I've got a list of elements. Hydrogen's one, carbon, nitrogen, oxygen, sodium, magnesium, potassium, calcium, manganese, iron, zinc. And there may be some more. I've got them listed. Where's sulfur? Sulfur, phosphorus, chlorine. So there's about 10 or 15, 20 that you need to learn that we'll go over. The most important ones are these four, and that's because they make up almost all of you. 96% of you is oxygen, carbon, hydrogen, and nitrogen. You also have, these are the ones you have to know, calcium, phosphorus, potassium, sulfur, sodium, chloride, chlorine, magnesium, iodine, and iron. And then there are a few trace elements, chromium, manganese, and zinc. Now, be careful when you're learning these atomic symbols that you don't just think, if it starts with a C, it must be a C, okay? Because carbon is C, okay? But calcium starts with a C, it's Ca. Phosphorus starts with a P, it's P, but potassium also starts with a P. This symbol is K. Sulfur starts with an S, its symbol is S. Sodium starts with an S, its symbol is Na. Why is that? Well, in this case, they went back to the original Greek or Latin, I think Latin terms for these. Potassium is actually kalium. Sodium is actually natrium. So you get the K and the Na. What about iron? Actually, ferrous. That's where you get the Fe. So you've got to kind of know a little bit about the root word to know where they got the atomic symbol. But those are the ones you're responsible for knowing. Okay, I just already talked about that a few minutes ago. I talked about neutrons, protons, and electrons. Skip ahead. Okay, molecules and compounds. Sometimes we use those words interchangeably when actually they don't mean the same thing. And a lot of times, and I'm guilty, I do that too. But in reality, a molecule is when you have two or more of the same atoms bonded together. A compound is when you have two or more different kinds of atoms bonded together. You'll always see hydrogen written as H2. You'll always see oxygen written as O2. Those are molecules. That's how they occur naturally. Compounds, again, water, it's two elements, hydrogen and oxygen. Salts, sodium chloride, HCl, that's hydrochloric acid. Sodium hydroxide, that's a base. That's also a compound. So anytime you see, two elements together, that's a compound. Two of the same element is a molecule. All right, when we talk about chemistry, we're going to talk about equations. We won't do as much this semester as you will next semester, but we will do some. All chemical equations are set up the same way. You have your reactants, which is what you're putting together, and then you have your product, what the end result is. So if you have two hydrogens then as your reactants, then the product is H2, which is a hydrogen gas. If you take 4 hydrogens and 1 carbon as a reactant, put it together, you will get methane. And so what's happening is you are making or breaking bonds. That's what's going on in chemical reactions, the formation or the breakdown of chemical bonds. When we talk about chemical reactions, they come in 3 forms. You're either making stuff or breaking stuff. Or sometimes you're just rearranging. Making, breaking, or rearranging. Synthesis is what you call making, decomposition or breaking, and exchange or rearranging. A and B are not elements. These are just for example only. Okay, so don't say, what is an AB? There's no such thing. Just for example. Somebody always asks me that. So if you put A plus B, you get AB. That is a synthesis. You're always making a bond. That word is anabolic. It's an anabolic reaction. It's making something. Biologically, a good biological example of that is making proteins. Okay, so you take amino acids, bond them together, and make a protein. All right, what if you took A, B, and broke it down? You're breaking those bonds. That's catabolic. You're breaking things down. So here's that protein again. So pretend that was steak. I'm eating the steak, goes into my stomach, and digestive enzymes are breaking it down. Now I've got my amino acids back. That's catabolic. You also see that in relation to blood sugar. We store blood sugar, we store sugar in our bodies, in our liver, as glycogen, but we can't really use that. So in order to use the glucose, these are glucose molecules, we stick those together as glycogen. To use it, we have to break it down into our individual glucose molecules. So that's decomposition, breaking bonds. What if you just exchange them? So in here you've got AB plus C, and now you've got AC plus B. So you see the B just kind of moved, and the C, they change places. All right? So you're breaking these bonds, and you're making these bonds. So you're making and breaking bonds at the same time. Let me go back. And you'll see this, for example, hydrochloric acid plus sodium hydroxide equals water plus sodium chloride. So hydrochloric acid, which is an acid, plus sodium hydroxide, which is a base, the hydrogen and the OH, the hydrogen ion and the hydroxyl ion come together to make water. So those bonds broke and these bonds were formed. These chloride and sodium, those bonds break and they come together and make sodium chloride, which is salt. So you can actually drink, if you put an acid and a base together, you wind up with a water and a salt, which is pretty cool. So again, that's an exchange reaction. You also see that when we talk about ATP. We're going to talk about that throughout the semester. ATP, when you put glucose and ATP together, basically what happens is this phosphate is transferred over to the glucose, and you wind up with something called adenosine diphosphate. It just has 2 phosphates. So you'll see these throughout the semester, these exchange reactions. All right. When we talk about chemistry, we talk about energy. Hopefully my voice is going to hold out. This is my 2nd hour of lecturing today. Talk about energy. When we talk about energy, we're talking about what it takes to do work. How do we put things in motion? We have kinetic and potential. Kinetic energy is basically energy in action or actually doing work. Potential energy is stored energy. So if I took this little stretchy thing, okay, and I stretched it out, that is potential energy. It has the potential to do something. When I let it go, it snaps back together, it moves, that is kinetic energy. So potential energy is stored energy, kinetic is energy in motion. There are different types of energy. There's chemical energy, electrical energy, mechanical energy, and radiant or electromagnetic energy. Chemical energy is those bonds we talked about. Every time those bonds are made and formed and broken, there's some kind of chemical energy that's either stored or released. Electrical energy, that is just the movement of charged particles. Okay, if you know anything about physics and electricity that goes on with your light, that's just charges moving. You say, well, who cares? We have no electrical energy in our bodies. Well, actually, we do. We do have electrical energy. Our nervous system works basically using electrical energy, and how it works is basically you have sodium, which is a charged particle. It actually moves in and out of the cell. And we'll talk about that in detail later. But it's actually that movement of these charged particles that are generating the electrical current that allows our nervous system to work. Mechanical energy, that's just actually moving matter. So I'm using mechanical energy right now, picking up my glass. And then we have radiant or electromagnetic energy. And these are things that usually have a wavelength, like light, UV light, X-rays. So right now I can see my board, that's visible light coming into my eye, going to my retina, and basically stimulating my retina to make a picture so I can see. UV light, we use that. That is what makes our skin darker. It causes our melanin to become, you get more melanin to make your skin darker. Or we use UV radiation to make a conversion to produce vitamin D. And we use vitamin D to help store calcium in our bones. So we do use UV radiation. These energy forms can be converted between each other. Okay, so you can convert one form of energy to another. But when you do that, it's not always real efficient. And usually what happens is you lose heat. A great example of that is a light bulb. Okay, so if you have a light bulb, you plug it into the wall, right? You plug it in, the electrical energy is coming down the wire, and the light lights up. You take an electrical energy and you've made radiant energy, visible light. A byproduct of that, because it's not real efficient, is that light bulb gets hot, gives off heat. So same thing happens in your muscles. You take an electrical impulse from your nervous system out to your muscles. Those muscles contract. They start to have mechanical energy. And the byproduct of that mechanical energy is heat. Your muscles generate heat when they contract. Okay. When you talk about chemical reactions, you'll learn real quick in anatomy and physiology, we are all about categorizing. We have to have all of these kind of categories. Okay, so here we go. One of the categories of chemical reactions are they're either exergonic, or endergonic. If they're exergonic, that means they release energy. If they're endergonic, that usually means they store energy. Exergonic reactions are almost always catabolic. They involve breaking something. Endergonic reactions are anabolic, or they are forming or making something. When we talk about chemical reactions, we have to think about some things that that will influence those reactions. What makes them work faster or slower? When you increase the temperature of something, you increase the rate of the reaction. Think about making iced tea. If you take iced tea, when does the sugar dissolve faster? When it's cold or when it's hot? When it's hot. So if you put the sugar in hot water, the sugar dissolves a whole lot better than it does in cold water. So that high temperature increases the rate of breaking down the sugar molecules or compounds. Particle size. The smaller the particle size, the faster it is. So let's do sweet tea again. If I drop a big sugar block inside my tea, it's going to take a while for it to dissolve. But if I drop fine sugar into my tea, it's going to dissolve faster. So the smaller the particle size, the faster the rate. The more stuff you put in there, the faster it is, okay? If I want my tea to be really, really sweet, and I put a lot of sugar in there, it'll be sweet really quick. If I just put a little bit at a time, it's going to take a while for it to get as sweet as I want it. Now, what's a catalyst? Sometimes we want to increase the rate by not changing the temperature, or not changing the particle size, or not changing the concentration. Okay, so let's think, for example, you've got some logs, and you want to burn them. You don't want to put more logs on there. You don't want to take away less logs. You don't want to use bigger logs. You just want to burn these logs. You could use a catalyst to make them burn. So you could throw gasoline on it, and then it would burn. And so a catalyst means you're going to make something occur faster without changing its temperature or changing the particle size or changing how much you have. And in biology, we call these catalysts enzymes. And they're really handy. The best example when we talk about enzymes is if you were to, let's say, there's an enzyme called lipase. Anytime you see the word or the suffix ase, A-S-E, that is always some type of an enzyme. So with lipase, lipids are fats. So lipase breaks down fat. So if you were to ingest a meal, a high-fatty meal, eventually the fats would break down. I mean, things deteriorate, they denature, or they rot or break down on their own, but it takes time. Well, I don't have all day long to digest that fat. I need it to go on through my system, okay? So you'll release things called lipases, and these are enzymes that will break down the fat. So they will break down faster. So I could eat a big fatty meal, and the lipases will come in there and break down that fat in a couple of hours. Without the lipases, that reaction would occur eventually, probably not in time for my stomach to go ahead and pass that food through my small intestine and out as feces, and the fat would just come right on through. So these cause those reactions to occur faster. And we'll talk about enzymes a lot as we go along. Okay, so that is the end of this lecture. And I'm going to stop this one, and then I've got one more chemistry lecture, but I'm going to do it as a different one. And hopefully it won't be quite as long.